There's a photograph sitting on a NASA hard drive right now that, if you understand what you're actually looking at, should make you uncomfortable. Not because it shows anything frightening, not because it's some classified anomaly, but because it quietly contradicts almost everything you were taught about the moon in school. And the people who took it didn't even need a special instrument to do it. They just needed to be in the right place, a place no human being had been for 53 years. For more than half a century, our understanding of the moon has been treated like a closed book. We had the Apollo rocks, sealed away in nitrogen since the early 70s. We had the orbital maps, the laser altimetry, the gravity surveys. We had that familiar pockmarked face we've all looked up at since we were children. The textbook said the moon was a dead, finished thing, a gray artifact in the sky, a museum piece. That story is starting to fall apart. And the photographs the Artemis II crew brought home, the first images of the lunar far side ever captured by human eyes in 2 full generations, are the wrecking ball going through the wall. This is what those 4 astronauts actually saw. Why it matters far more than the news cycle suggested. And why nearly everything you thought you knew about our closest neighbor is about to be rewritten. On paper, Artemis II was supposed to be boring. That's not me being disrespectful. That's literally what NASA was selling. A shakedown flight, a test drive, for astronauts strapped into an Orion capsule that the crew themselves nicknamed Integrity. Commander Reed Wiseman, pilot Victor Glover, mission specialist Christina Koch, and Jeremy Hansen of the Canadian Space Agency. For people, 10 days, 1 job. Prove that the spacecraft works. Launch from Kennedy Space Center on April 1st, 2026. Climb out on the Space Launch System rocket. Swing onto a free return trajectory that loops behind the far side of the moon and uses lunar gravity to slingshot you back home. Don't enter orbit. Don't land. Just verify the life support, the heat shield, the comms, the re-entry profile. Splash down in the Pacific. File the paperwork. Move on to Artemis III. That was the plan. But here's the thing nobody on the procedure side of NASA fully accounted for. The crew was carrying something Apollo astronauts in 1972 simply did not have: modern cameras. Sensors with high dynamic range capable of pulling detail out of deep shadow that 1970s film could not have resolved if you'd given a year. Handheld bodies with 400mm lenses sitting in zero gravity, strapped to the wrist of an astronaut whose only job for several hours was to look out the window. So when Integrity finally swung behind the moon on April 6th, the crew did the only thing any human being would do with that view. They started shooting, and they kept shooting for 7 hours. Working in shifts, the 4 of them captured something close to 10,000 individual frames. Their closest pass to the lunar surface was just over 4,000 miles. At their farthest point from Earth, they were sitting 252,756 miles out, breaking the distance record Apollo 13 set back in 1970, and turning these 4 into, by definition, the most distant human beings who have ever lived. While they were out there, 2 things happened that have no precedent in the history of spaceflight. First, the geometry of their orbit took them straight through Earth's shadow at a moment when the Sun, the Moon, and Orion all lined up on the same axis. The crew became the first human beings ever to witness a total solar eclipse from deep space. They watched the Sun disappear behind a darkened moon for nearly an hour. They studied the corona, the Sun's outer atmosphere, glowing around a lunar edge in a way no observer on Earth has ever seen with their own eyes. And second, while they were on the dark side of the moon, with no daylight glare to wash out the surface, they caught the faint flashes of meteoroid impacts hitting the lunar regolith in real time. Tiny rocks, most of them smaller than a marble, slamming into the surface at thousands of miles per hour, releasing brief pinpricks of light visible only because the conditions were perfect for once in human history. Either of those would have been a career-defining observation. Neither of them is the reason this mission matters. The reason this mission matters is the far side itself. Picture yourself floating alongside Integrity at the moment of closest approach. The moon is rolling underneath you, slow and silent. And what you're seeing through the window is something fewer than a dozen human beings in all of history have ever seen with their own eyes. The entire far hemisphere of the moon, lit at a sun angle no Earth-based telescope could ever produce, scrolling past you at lunar speed, heavily cratered, rugged, Ancient, completely, almost shockingly different from the face we grew up looking at. For about 40 minutes during that flyby, Integrity was on the wrong side of the moon for radio signals. No comms with Earth. No mission control whispering procedures into their headsets. Just 4 human beings in a metalkin, more isolated than any people who have ever lived. Wiseman later described the experience as something that bent his mind. Not feeling like he was sitting inside a spacecraft, but feeling like he had been transported. Looking back through one of the small windows at the very moment Earth itself dropped below the lunar horizon, shrinking into a tiny blue crescent and then disappearing entirely. That photograph, the one the crew called Earthset, is already, less than a month after mission, one of the most important images in the history of human spaceflight. Apollo 8 gave us Earthrise back in 1968. The famous frame where our blue marble planet seemed to climb above a gray lunar foreground. It became, almost overnight, one of the most reproduced photographs in human history. It changed how a generation thought about Earth. Artemis 2 gave us the inverse. Home not rising, home setting, home falling away. And what was left behind in the frame, after Earth was gone, was the face of the moon that no person on this planet can ever see directly from where we live. That face is the heart of one of the deepest unsolved mysteries in planetary science. Here's what's strange about our moon. The side we see, the near side, has these huge dark patches called Maria, smooth, flat plains where molten basalt welled up from the interior billions of years ago and flooded gigantic impact craters. They cover roughly 31% of the near side. They're the dark patches that, if you squint, look like a face. The man and the moon. On the far side, those dark plains cover only about 2% of the surface. Almost nothing. Instead, the far side is a chaotic landscape of overlapping craters, older terrain, thicker crust, and impact basins that for some reason never got resurfaced by lava the way the near side did. 2 hemispheres of the same world. Same age, same parent material. 2 completely different geological histories. Scientists call this the lunar dichotomy, and it has been bothering planetary scientists for 60 years. Average crustal thickness on the far side is something like 20 kilometers greater than on the near side. The chemistry differs. The volcanic record differs. And every theory anyone has come up with for why this happened ends up running into a wall. The first serious explanation was the simplest one. Maybe the near side, just a thinner crust, so magma could break through more easily and resurface the terrain. That worked beautifully on paper, until lunar orbiters mapped the South Pole Aitken Basin on the far side properly, and found that this basin actually has the thinnest crust on the entire moon. By the thin crust theory, the floor of that basin should be a sea of frozen lava. It isn't. Only a few percent of it has ever been resurfaced. Theory 2 involved a family of elements that scientists nicknamed KREP, short for potassium, rare earth elements, and phosphorus. On Earth, these things are scattered relatively evenly. On the moon, they're concentrated almost entirely on the near side, packed into a region called the Procellarum KREP terrain. Several of these elements are radioactive. Radioactive elements decay, and decay produces heat. More heat means more melting, which means more volcanism. And that lined up with what we observe, until you ask the next obvious question. Why is KREP concentrated on the near side in the first place? Nobody has a clean answer. Then came the impact hypothesis. Maybe early in the solar system, a smaller second moon formed alongside ours, drifted into us at low velocity, and piled extra crust onto the far side. Or maybe a giant collision on the near side dug out a megabasin and shoved KREP material to one hemisphere. Recent computer simulations from research groups at Brown University, the University of Munster, and Macau University of Science and Technology have shown that a slow-velocity impact from an object roughly 780 kilometers across could actually reproduce the asymmetry we observe today. The math checks out. What we've never had is a smoking gun, until very recently. In June of 2024, China's Chang'e 6 spacecraft did something nobody else had ever done. It landed inside the South Pole Aitken Basin on the far side of the moon, scooped up nearly 2 kilograms of lunar material, and brought it home. The first physical samples from the lunar far side in human history. When Chinese researchers ran isotopic analysis on those rocks and compared them against Apollo samples we've had in storage for half a century, the results were genuinely surprising. The potassium isotope signatures were different. The sulfur was different. The iron was different. The chemistry of the far side mantle, as preserved in those samples, looked like it had been altered by something massive, something more energetic than the standard models had assumed. The implication was that whatever ancient impact carved out the South Pole Aitken Basin didn't just punch a hole in the moon. It changed the deep interior of the far hemisphere in a way the near side was protected from. And that single event might be the root cause of the dichotomy we've been chasing for 60 years. The Artemis 2 images are now feeding directly into that ongoing analysis, not because any single photograph is going to solve the lunar dichotomy by itself, but because for the first time since 1972, we have direct human observation of that terrain, combined with modern orbital data from NASA's Lunar Reconnaissance Orbiter, Japan's Selene mission, India's Chandrayaan probes, and the entire Chinese Chang'e program. 10,000 new frames, captured at angles, lighting conditions, and dynamic ranges no robotic mission has ever produced. One of the very first images released to the public shows Vauvilov Crater, sitting on the rim of the older and larger Hertzsprung Basin on the lunar far side. The image was taken handheld at 400 millimeters. The long shadows along the terminator, the boundary line where lunar day meets lunar night, accentuate the structure of the crater walls and the ejective patterns in a way that overhead orbital photography simply cannot. Geologists who have stared at this region through orbiter data for decades are now seeing it in human-eye dynamic range, with shadow geometry that reveals depth, layering, and structural detail that nobody had ever quite resolved before. And here is where the story really starts to bend. For the last 15 years, evidence has been quietly accumulating that the moon is wetter, more chemically active, and stranger than anyone seriously believed possible. Back in 2009, India's Chandrayaan, one mission detected hydroxyl signatures across broad regions of the lunar surface. The same year, NASA deliberately crashed an instrument called LaCrosse into Cabeus crater near the South Pole, and the impact plume confirmed the presence of water ice trapped in the permanent shadow there. In 2020, the Sophia Airborne Observatory detected molecular water on sunlit parts of the lunar surface, which on its face violated everything we thought we knew, because water and sunlight should boil off into space within hours. More recently, Chinese researchers identified microscopic glass beads scattered across the lunar surface, each one acting like a tiny spun for hydrogen particles delivered by the solar wind. Collectively, those beads might be holding hundreds of billions of tons of water across the moon as a whole. The picture that is slowly coming to focus against decades of orthodoxy is that the moon is not a dead rock. It's a planetary body with a complicated, ongoing relationship with water, ice-locked in permanent shadow. Hydrogen raining down from the sun glass beads acting as microscopic reservoirs. A system nobody predicted in 1972. And yet, and this is the part that should bother you, the textbook understanding of the moon was built almost entirely from 6 Apollo landing sites. All of them on the near side. All of them in a narrow band near the equator. Imagine landing 6 probes in the Sahara Desert and using their data to write a complete geology textbook about Earth. That is functionally what we did with the moon. The Artemis 2 images matter because they're the first human-captured visual data of the far side since that era. And the far side is precisely where our current model breaks down hardest. There's a piece of this story that almost didn't work out, and it deserves a moment. When Integrity slammed back into Earth's atmosphere on April 10th at nearly 40,000 kilometers per hour, the capsule was relying on a heat shield made from a material called Avcoat, the same material family used on Apollo. After Artemis I, the uncrewed test flight back in 2022, engineers have found that Avcoat behaved unexpectedly during re-entry. Pieces had eroded loose in patterns the simulations did not predict. NASA spent 2 years investigating, running arc jet tests, debating whether to fly Artemis 2 with the same shield or hold the mission for a redesign. In the end, the agency decided to fly with a modified re-entry profile, steeper, shorter, designed to limit total heating time. The capsule came in hot. Plasma wrapped the hull. The crew pulled close to 4 Gs of deceleration. For about 6 minutes during peak heating, communications were dead. then the drogue chutes deployed, then the mains, then splashed down in the Pacific off the coast of San Diego at 5:07 in the afternoon Pacific time. The heat shield did its job. Every photograph, every data point, every observation from that flyby came home only because that piece of hardware held together. Artemis 3 is going to fly a refined Avco formulation, but Integrity's clean return is what cleared the runway for everything that comes after. Artemis 3 is currently scheduled for 2027. It won't land on the lunar surface. It's a test of integrated operations with commercial landers in low Earth orbit, including demonstrations with SpaceX's Starship and Blue Origin's Blue Moon lander. Artemis 4, currently targeted for 2028, is a mission that's supposed to actually put boots back on the lunar ground. And the targeted landing zone is the lunar South Pole. The South Pole is not a sentimental choice. It's the region where permanently shadowed craters hold confirmed water ice. It's the boundary zone where the thicker far side crust transitions into the thinner near side. It's where the geology is strangest, the volatiles densest, and the case for sustained human presence is strongest. And the United States is not the only player at that table. China's crewed lunar program is targeting 2030 for its first astronaut landing. The International Lunar Research Station, a joint China-Russia project, is scheduled to break ground in the early 2030s in the same general region NASA is targeting for Artemis 4, which means the next decade is going to look more like the 1960s than anything we've seen since. Two superpowers racing to build a permanent presence on the moon, both targeting the same patch of real estate. Both well aware that whoever lands first and builds infrastructure first gets to write the unofficial rules for everyone who follows. Water ice, once it becomes accessible, can be split into hydrogen and oxygen. Hydrogen is rocket fuel. Oxygen is breathable air. Whoever controls lunar water ends up controlling the economics of deep space. In that light, the Artemis 2 photographs are not souvenirs. They are reconnaissance, maps of the battlefield, sketched before the battle begins. Two small craters on the far side were given names during this mission. One is now called Integrity after the spacecraft. The other was named Carol after Reed Wiseman's late wife, who died in 2020. 5 years after losing her, Wiseman carried her name to the far side of the moon and placed it on a feature that will outlast every country currently on this planet. Long after NASA exists, long after the United States exists, long after English is a spoken language, that crater will still be named Carol. It is somehow the smallest detail of the entire mission, and also one of the most human. The crew also brought back something else, a photograph taken on the way home, looking back into deep space, of our own galaxy, the full spiral structure of the Milky Way, captured in a single frame. From inside the solar system, you can't normally see our galaxy this way. There's too much glare, too much atmosphere, too much light pollution. But out past the moon, with nothing between the camera and the void, our home becomes visible as what it actually is, a flat disk of 200 billion stars, seen edge-on, with Earth sitting roughly halfway out along one of its arms. For a few minutes, for people looked through a window and saw their full address, not the neighborhood, the whole galaxy, that, more than anything else, might be what Artemis 2 actually represents. Apollo was about proving we could get there. Once we proved it, we stopped going. For more than 50 years, the moon was something humanity had visited, past tense, a completed item. Artemis is meant to be different. The stated goal isn't to visit, it's to stay, a permanent base, sustained presence, a staging ground for missions to Mars. So when you look at those 10,000 photographs, the question they're really answering isn't what do we see. The question is, where do we put the first human outpost beyond Earth, and how do we survive once we're there? The moon we thought we knew was a convenient fiction, a gray, scarred, silent thing, useful mostly as a symbol of what humans could do when we decided to try. That fiction is dying, and what's replacing it is stranger, wetter, more geologically alive, and more scientifically valuable than anyone watching the last Apollo liftoff in December 1972 could possibly have predicted. It started, in a very real sense, with 4 people in a spacecraft called Integrity, looking out a window, taking 10,000 photographs of a place no one had seen with their own eyes in half a century. The The moon was never dead. We just stopped looking. And finally, after all this time, we've started again. Thanks for watching Astrion. If you got something out of this one, the subscribe button does more than you'd think for a small channel like ours. I'll see you in the next video.